conservation of momentum, I now want to focus on two body collisions in one dimension. One of the things here is I said that momentum is conserved in collisions. That means that the momentum does not change before or after a collision within a system. The system must reorganize itself to conserve V center of mass. So here's what we know. So there are two types of collisions. These collisions are called, there are elastic collisions. And elastic collisions, what it really tells us here is that there is no loss in energy within the system. And we have not even defined what energy is. And then we have things that are called inelastic. And here, what we find here is that there's this energy loss within the system. So what do I mean about this word energy? Well, it's a slippery word the way we're using it. So if I look at examples here, so if I have a perfect elastic collision, here's what I would find here. I would drop a ball. Okay, let's say that I take my ball and I'm going to drop it right here. And then what I'm going to see here is that I'm going to drop it onto the ground. So then the ball's going to come down here and there's going to be a collision. And what we focus on is we focus on right before the collision. So we need to focus right before collision. So that picture of me dropping a ball onto the floor is not a good enough picture. So what we want here is we want this picture. So now the ball is about to hit the ground. And so now we're seeing that this ball is moving in this direction like that. So this is what we call before the collision. Okay? This is before. And then after, we compare the after picture. And so now the ball is now moving, let's say, in the upwards direction here. We don't know what its momentum or its speed is, but it's headed in this direction. This is what we mean by after. So now I have a collision. So what do I mean by a perfect elastic collision? It tells me that there is no sound upon the collision, and it reaches its original height. So when I look at this, remember, this is the most important picture right here, right? This is most important. But when we're trying to decide whether something is elastic or inelastic, here's what we find. We take this picture, and when we drop the ball, what actually happens here? The ball comes down, it collides, and then afterwards, the ball reaches the same height after the collision. So it comes down, it gets to here, and now it starts to go back up, right? And so now we see that this thing starts to go back up, and you could see that the ball reaches the same height as initial drop. So what that tells us here is that there is no energy loss to sound, heat, to sound and heat. And so what I mean by heat here, this is the heating of ground and ball. So the ball does not heat up. And here, of course, you can't hear. So all of the energy, so then this tells us here is that all the energy stays with the ball. That's what we call a perfect elastic collision. But the vast majority of the collisions are inelastic. So most collisions are inelastic. Again, if I think about examples, what happens if you drop a golf ball on a floor? That implies you hear it. And because you hear it, that immediately tells you it's inelastic. There's some energy loss to sound. And at the same time, you're also noticing that the ball will not come up to the same height. So then the golf ball does not return to the same height. So if I drop the ball again, and then this is the ground right here. So as I drop it in this direction here, you're seeing that the ball will not get up to its original height. So you can see here is that there is a height change, telling you that if there's a height change, what's most likely the cause or the biggest cause here is that there was heating up of ball and floor. So elastic collisions keep all of the energy in the motion. Inelastic transfers it out. So let's go look at this thing here. So what I want to do now is that I want to start to look at some examples and look at multiple situations and try to draw pictures of what's going on. So here, I now want to organize How do I spell organize? Organize various collisions using bar diagrams, momentum bar diagrams. Okay, so here we go. So the way I'll organize it is that I'm going to start with elastic collisions. And it turns out that mathematically, they are more difficult to deal with, but conceptually, it's easier to follow. Inelastic collisions turned out to be, in general, more challenging. So let's start with case one. So our first case, which is, in my opinion, the easiest one, is called elastic collisions. So these collisions are perfect in that no energy is transferred out of the system. It all stays with the motion of the objects. So this is an extreme case, okay? This is an extreme case. So here's what we see here. So you could imagine that I have blocks, okay? So let's imagine that I have this block coming in. And let's color code these. Let's say that this is going to be the red. And all the reds will be block 1. And then I'm going to have block 2 here. And let's say that all of these blocks are going to be green. And I'll call that 2. And what we're going to see here is that each of these blocks are going to have some momentum that we don't know yet. So this guy's going to have some momentum, P initial coming in. This one's going to have some momentum, P2 initial coming in. And we're going to focus on our system here. And because this is the only forces within our system, we immediately say that the external force is 0, which then means that momentum is conserved. That's what we want to focus on. So we need to look at the picture of before, and then we want to compare the picture of what happens afterwards. So when I think about what happens afterwards, of course, there's a collision, but afterwards, what we're imagining here is that now the momentums of these blocks are now going to readjust themselves, right? They're going to readjust themselves. So then I'm going to have some other different momentum for each of these objects. And again, everything stays within the system. So once again, the momentums of the individual objects must adjust themselves to conserve P total equal to a constant, or V center of mass equal to a constant. They're one and the same thing. So because of this, then it says this, that the momentum of the system initially must be the momentum of the system in its final state, which means I have P1 initial, P2 initial equals to P1 final plus P2 final, and these guys are vectors. So we have to pay attention to their sign. This is what we mean by momentum conservation. Right? So this is conservation of linear momentum. Okay, so here we go. Let's go look at this thing here. So I'm going to look at a couple of cases here to get a sense of where we're at. So the first one that I'm going to look at is that I'm going to look at a system of equal masses. Okay. So if I have equal masses, then that means M1 is equal to M2. And I could imagine that I'm actually shooting billiard balls, because billiard balls have the same mass, but I'm going to stick with blocks because they're just easier to draw. So this is what I mean by equal masses right here. So I imagine that we have two billiard balls going right at each other. You know what? I think I'm going to stick to blocks. I think they're easier. So what actually happens here? So what I see here is that I want to draw the situation. So I have a block, not a block, but a ball. Yeah, I'm going to draw balls. So I'm going to have a ball. And this is my red ball. And I'm going to call that one 1. So what do I know about this guy? This guy is coming in, and it has some initial momentum of the system. Then I have a billiard ball that's exactly the same size. And this is 2 right here. And what I'm going to say here is that the billiard ball 2 is stationary. So now I focus on my system. Because I have a system and I ask, are there any forces other than the collision forces? The answer is no. These two are going to interact. So then what I'm going to say here is that this before picture, what I'm seeing here is that the external force is equal to 0, which then implies that the total momentum of the system has to be a constant. How do I draw that? Well, according to the bar diagram, here's what I see. I have the momentum of billiard ball 1. That's the total, that's the momentum of P1. And then we ask, what is the momentum of 2? Well, the momentum of 2, we already see is 0. So what that means here, since the total momentum is a constant, it has to do, this is my constant right here. It cannot change. So now I come to afterwards. So when I look at the momentum before is going in which direction? Look at the direction. It is moving to the right, and it has that height right there. It has that height. So that means this implies here that the total momentum must continue to move to the right. But look what happens to P2 here. P2 initial is 0. So what happens here is that the momentums must adjust, but we also find out that there's an exchange of momentums. So what ends up happening here is that momentums also must exchange their momentums too. So in other words, 1 and 2 are going to exchange their momentums. In other words, what I'm saying here is that when I look at this thing, the momentum of 1 after the collision is 0. And then when I look at the momentum of P2 afterwards, it's exactly the same size as P1. What did they do? They exchanged their momentums. So therefore, 1 now has a final momentum of 0, and 2 now has a final momentum that's equal to the momentum of 1 initially. And that's what would happen within the system. They adjust themselves and they keep the total momentum going to the right, and they also exchange their momentums. Okay, so now let's go to another example. So the next example I want to do here is that I want to imagine that I have massive target a massive target. So what do I mean by a massive target? I'm going to imagine that M1 is much, much smaller than M2, which means I imagine that what I'm shooting here is that I'm going to shoot a golf ball at a bowling ball. And let me try that again. So what does momentum have to say about this collision here? So the first thing that we got to think about is that what happens if we actually throw a golf ball? So let's physically try to think about this. So imagine that we throw a golf ball. Here's my little golf ball. And we're throwing it at a large bowling ball. So in this case, we see that here's our 1, and then here's our 2 here, and we're throwing this guy with some momentum initially going to the right like this. What do you think is going to happen? Well, right away, if I make this my system here, we could see that beforehand, what's going to happen? Which object do you think, what's going to happen to the golf ball? Well, what we expect here is that the golf ball is going to bounce back exactly at the same direction that it came. By the way, I don't know if you've ever thrown a golf ball at a bowling ball. You want to be careful. That golf ball is so unpredictable. Oh, and it comes off pretty crazy. So what we expect here, we expect the golf ball does not change speed much. In other words, I would say that the initial speed of the ball is going to be approximately to its final speed. It's going to be slower, but I would expect that it's going to be roughly the same value and magnitude. It's sort of like if you take a golf ball and you throw it at a hard, smooth wall. It comes back pretty fast. The bowling ball should hardly move forward, right? That's kind of what we would expect it to happen here. So now, if I look at this picture, what do I see momentum-wise? Okay. So I have a momentum. Let's say that this guy has this amount of momentum initially. So this is the momentum of P1 initial. And because the bowling ball is fixed in place, we know that it has zero momentum. So once again, we see here that the total momentum, which is equal to a constant in this situation, will not change no matter what happens afterwards. So now what happens? We see that the ball, our guess is that it's going to bounce back with roughly the same speed. So if it bounces back with roughly the same speed, look at the number of squares. Beforehand, it's 3. So then afterwards, I would say it's going to be less than 3. Let's say that we say it's 2.5. Look at what happens here. So now I have P1 final that's going to be negative. So what I'm seeing here is that the momentum is going to the right here. Now the momentum is going to the left. So which ball do you think has the biggest momentum? The golf ball, which almost loses no speed, or the bowling ball that moves slowly forward? Well, according to conservation of momentum, we have to conserve momentum. So think about the impulse momentum theorem. The impulse momentum theorem says the following thing, that what does ball 2 have to do? What does the bowling ball have to do to the ball? It has to stop the golf ball. So at the minimum, part of the momentum has to go where it has to stop the golf ball. So right away, this is where the bowling ball stops the golf ball. Remember, I'm using this as the impulse momentum type thinking. But then, what do we have to do? We have to increase the speed of the ball. By the way, I did this incorrectly. Let me adjust this. This is what we have to do. We had to, it's the initial speed that we had to do this to. And now we had to speed up the ball. So if we had to speed up the ball, now it goes up 2.5 blocks. So when you're looking at this thing, you can see that the momentum of P2 afterwards is enormous. So what we're seeing here is that the reason why the momentum of the bowling ball is so huge is that we can have momentum large two ways. I could have a momentum that has a high speed versus a momentum with a big mass. It turns out that the bowling ball has a big mass, so it doesn't have to have a high velocity in order to have a big momentum. So this is the bowling ball after the collision. It has a big mass, but it has a small speed. So then afterwards, we see here that this guy has a smaller momentum, but roughly the same. And then the bowling ball is then going to barely move, right? It's going to have a slow speed, but it's going to have the same momentum afterwards. So picture-wise, it has to look like that. So the lion's share of the momentum is with the bowling ball, not the golf ball. So we have one more example that we want to go through, and then we should go through a different example. Then we'll do an example. So the next one that we want to do here is that we just did a massive target. What happens if we have a massive projectile? So now we want a massive projectile. So if I look at what we wrote last time, we had M1 much smaller than M2. So I got to write the same thing. So now I'm going to have M1 much bigger than M2. But now what we're going to do here is that we're going to shoot a bowling ball at a golf ball. So now let's go physically interpret the same thing. What do we expect when we physically interpret what's going on? Picture-wise, you could imagine that I throw my bowling ball. And I'm going to throw it at a stationary golf ball. So when I'm looking at this little guy, compared to this one, we can see that this guy is coming in with some initial momentum like this. So again, I want to choose my system this way because now the power of choosing this is that we know that the momentum of the bowling ball is this big right here. And because the momentum of the bowling ball is like this, and we have a stationary golf ball, the power of conservation of momentum is these guys have to be the same. Right? That's my total momentum, or V center of mass, remaining fixed. That's what we mean by that. So what do we expect to happen in this situation? Well, what we expect here is that the bowling ball is not going to lose very much speed. So we expect the bowling ball to not lose much speed. I mean, it's not the same, right? But if I have a Mack truck hitting a moth, the deceleration of that Mack truck is almost zero. So if the bowling ball versus the golf ball is analogously the same here. So in other words, we expect that the initial speed should be almost the same as the final speed. So if I go to my bar diagram, what I'm seeing here is that most of the momentum stays with the bowling ball. So you can see here that I left a little tiny gap up here. So how much momentum does this golf ball actually get? You could see that it's just this little tiny bit that it's getting. These momentums have to adjust themselves to keep the total momentum fixed for the system. So if I look at this thing, we imagine then that the bowling ball essentially has P1 initial equal to P1 final. And then what do we expect of the golf ball's momentum? Well, it's going to be tiny, right? This is going to be a really tiny momentum. But the question is, how big is this momentum going to look like? Well, it turns out that if the bowling ball stays fixed, it turns out that the speed of the golf ball is roughly twice the speed of the bowling ball. So it turns out that the speed of the golf ball is about twice the speed of the bowling ball. And the way we can see this here is that if we draw a picture here. So what we want to do here is that to physically see this, let's change our frame of reference. So what I'm seeing here is that I'm looking at the bowling ball right now. And what I'm seeing here is that the bowling ball is coming in with some momentum P initial. And now I have my little green golf ball right here, which is of course stationary. From this frame of reference, I'm going to look at this guy from what is called the lab frame. So you are watching it from this frame. But now what I want to do here is that I want to jump onto the bowling ball. So if I jump onto the bowling ball's frame, then what I see here, to me, the bowling ball is not moving. So in this frame, which tells me here that the bowling ball does not move. So what I see here is that look what happens here. What happens here is that now I have my golf ball that's moving towards me now. So what is the speed of the golf ball here? Well, if I look at the speed here, it has to have some initial momentum that's looking like this. Okay. So this is the before. But wait a minute. this is now a massive target. But we've studied the massive target. And what does the massive target says here? That the speed of the golf ball coming in is actually about the speed of the golf ball coming back. So now what I see here is that in this situation, if I look at what's happening to the speed of the golf ball, what I'm seeing here is that this guy essentially leaves with the momentum effectively of the same value that it has initially. So if I start to look at this thing, if the masses are the same, and remember, I'm on this frame. So if the masses are the same, and this is again afterwards, so if I look at the change in momentum of 2, I'm going to get what? I'm going to say that over here, I'm going to call this my negative direction. I'm going to call this my positive direction. So look at this. This is going the positive. So then this should be, it should read P2 final minus P1 initial. And these guys are vectors. So now let's look at what happens here. P2 is in the positive direction. So I'm going to come in here and I'm going to say, this is in the positive direction. Now I have a negative, but the negative direction tells me that I'm also going to have a negative of P1 or P2 initial. You know, I'm getting my signs all messed up here. Or my notation. My notation's all screwed up. It should be P2, and this should be P2 initial. But there's a minus sign because this guy is leaving in the minus, it's initially headed in the minus direction. So then this tells me here that this really equals plus P2 initial plus P2 final, which means then that these guys are essentially moving the same speed. So if it comes in and out, then what you're seeing here is that then V2 initial is about the same as that. You know, these details are not so important. What is important is getting this picture right. That's what's important. So we now covered 3 things. We talked about equal masses, the exchange momentums, massive target, golf ball hits a bowling ball. There's an exchange of momentums again. And then here, I have a massive projectile. There's an exchange of momentums again.